we learn about something new after the break. Okay. Now, 3.5, conservation of force and potential energy will be the last part of chapter 3, right? So you are familiar with the conservation of force and potential energy, or from the word itself, you know that conservation of force means um, all the force equal to zero, or you cannot destroy the force, right? And also the energy also, right? So energy can change from kinetic to potential to mechanical and so on. Yeah. So the definition of conservation of force, as you can read from here, basically you just say that um, um, it it used the concept of work to define the conservation of force, right? So if the work of the force is perpendicular, independent to the path and depends on the force initial and final position, which this is the definition of work. It is the work, right? The work is force and displacement. So if the force and displacement, they are the same direction, or then um, you can put them as conservation of force, right? So, so two example of conservation of force here is one either particles and the one is a spring. So if you look at particles, so the work done by the particles that fall down from a sky because of the gravity, so the work done by the weight itself is um, the work done by the weight itself that we've seen in one of the example previously is you take the force of the weight multiply by the displacement, then it become work. Right. Another one is okay, so this is just an illustration. The balls fall, so you get the displacement. Another one is a spring. Right. Spring, if you pull a spring, it can be either fluctuating from A to A, right? From rest is 0, but the spring, when it go up, it move to positive A, but if you move down, then you get a negative A, for example. Yeah. So this is the definition of conservation of force. So basically, you confine what is the definition. You go back to definition of work, right? So you focus on force and displacement. Then you fall under conservation of force. Okay, so for this module, I won't ask you about definition. I won't ask you the ask you to write the paragraph long essay definition, but I will expect you to show your understanding in your answer through mathematics equation, right? For example, acceleration A equal to dv over dt. So this kind of short equation I'm expecting in your answer, right? Rather than you write all this lengthy explanation, all right? So another one is that if you if you put an object and then you lift the elevation of the object, so this object will slide, right? Will slide along the surface, right? So the work can be done by the object as long as there is a force, there's additional force in the system that make the object to move. That's why we apply the F equal to ma equation, right? When we have excess force in the system, right, you will create a motion, right? That defined in the Newton law. So there's one tutorial question, particular test on that one. So you go back to the previous slides. So in the tutorial question, it gives you some forces, then you calculate. Then the forces is excess, means there's more forces in the system. It's not equal to 0. So there are some motion expected in the question. Okay. In this case, when you have a friction, right? When you have friction, work done by the friction force depends on the path, means the longer the path, the more friction force you have. So in this case, the friction force is not conservative. Friction force are not conservative because the longer contact surface you have, or the more contact surface you have, the greater work done by the force. Okay. All right, so this one is you have to be careful every time you have a friction. You have to know friction force is not conservative. Because according to definition of conservation of force, it say that if the work is if the work of a force is independent of the path and only focus on the force initial and final position, then it fall under conservation of force. Friction force do not meet this definition. Friction force depends on not the position, but it depends on the displacement of the contact surface it have. Right? This one, it depends on position and force, then fall under conservation. But if the scenario like friction, it depends on displacement, right? So that's why special highlight the friction force as non-conservative. Yeah. Next, just a recap of what you have understand, what you have learned before, the potential energy. Potential energy that you learn in physics class is mgh, right? Mgh, or in this case, because we are using datum, so datum, if you refer to datum, above datum, as you see from the arrow here, above datum with the arrow head pointing direction, you get a positive y. So those that below datum and you follow the arrow pointing, it will become negative y. All right. So above datum, you get positive. Below datum, you get negative. So the weight will always positive. All right. The weight will always positive, W. The force of the weight will be positive. All right. So what do you mean? So if an object, you lift the object from the datum to a certain height, or in your physics, you label as elevation h. In this case, we label as y. So if there is a positive distance from the datum, you get a positive energy there. You charge the object with energy as you go higher and higher. So you have equation of W and Y. Okay, W and Y. So yeah. So in general, Y is a positive, upward positive. So the gravitational potential energy of the particle weight is given by this equation. So this is what you're familiar with, right? So in your physics or in your statics, you always have a positive elevation, right? However, when you come to engine dynamics, you need to be careful on the datum position. Yeah. In your statics module or in your secondary school physics, your datum always below the object. However, for this module, we will play around with the datum, right? So you need to be careful on the datum. So if the datum is here, but the object is going down from the datum, then you get a negative energy. Just take care of the datum. So this diagram tell you what is the effect if you change the datum. The energy is still same. I mean, the magnitude of energy is still same. If you don't change the elevation, positive y and negative y, you still get the magnitude of W and Y or MGH. However, if your object going down, you have a negative energy there. If your object is above the datum, then you charge up, right? You charge up the energy. So before you solve for potential energy or energy question in chapter 3, be careful on datum. If your datum is given and your object is start from a position above the datum, then you get positive energy. If you're given a datum but the object start from a position below the datum, you get negative energy. Right. Next, once we know about potential energy of gravitational acceleration, then the next one in engineering devices, we use the laws of spring in our devices nowadays. So you're familiar with spring. Spring is always linked with the spring constant, right? So the derivation of spring energy, right? Potential elastic energy, we use V sub E, okay? V sub E, or in your test, if you forget what is the symbol, you can just write elastic potential energy or energy of the spring, potential energy of the spring equal to half Ks squared. S is a displacement that you pull from datum again. You see this line? Okay. So if the spring do not charge anything, means you stay at the unstretched position, means at the rest, the energy is zero. The energy that inside the potential, the potential energy inside the spring is zero. In this case, we use capital V sub E to represent elastic potential energy. So when at rest, energy is zero. And if you pull, you stretch the spring, you become positive energy, means you charge up the energy. You get positive half Ks squared. Right? And the spring potential energy, when you charge up, you're always positive, right? So in this case, for a spring, if although there's a datum line for spring, if you compress it, you also charge up the spring. Okay, you supply energy to the spring. You charge up the internal energy. You charge up the elastic potential energy for spring. No matter you pull or you compress, you both give you positive energy. That's why I put a remark with the red box here. Take care of that. There's a differences between spring and gravitational potential energy just now. Okay, there's a differences. Just take note on gravitational force. It be gravitational potential energy depending on your datum. Above datum get positive, below datum you get negative energy. However, when it comes to spring, it always negative, no matter you pull or compress. rest you can read over here. Okay, you learn about the derivation of this spring energy in earlier in your, I think in your statics last few chapter, right? But here we just apply the energy. Yeah. Okay. So we have studied gravitational and spring just now. So we can use an equation, we call it potential function, to refer to either gravitational force or spring. Huh? So in general, if you have, if you want to calculate an object falling from somewhere, referring to a datum or a spring, you can write an equation, a general equation of the whole system. Potential energy equal to gravitational force plus spring. Okay, so this equation only works when that particular object subject to gravitational force and also spring force. Okay, so there are two. So there are two cases here, right? But if you, it depends on which scenario you fall in, right? So if that object, but normally, if you see spring, when you see spring, you see datum. You need to combine the potential energy of both. But if the question only give you something falling from free fall from the sky, referring to a datum, then you only have potential energy of the gravitational forces. This equation only works when you have two scenarios happen at the same time. Work definition still same like what we learned. All right, what is work? Work is force and displacement. Force and displacement, they must be the same. And this one talk about the work done by the conservation of force. So so you get this one, V1 plus V2, something like that, right? So it depends on how it moves, right? You will look at example about this one. Then this one is about weight on the spring itself. So I think you're familiar with this diagram. Spring attached to an object, and that object has a mass. Usually the mass of the spring will be ignored in your analysis. So the only that affect the motion of the spring will be the weight and also additional forces charging the spring. Okay, you have two forces. One is the forces charging the spring. In this case, in this diagram, the force is pushing the spring. So you have a spring force here. And remember, there's a datum. So when you see datum line, you need to refer either is above the datum or below the datum. Yeah. So if gravitational potential energy above datum, you get positive energy. If your datum and the object is below, you get negative energy. Yeah? So just need to take note. Spring always positive. Spring energy, no matter you compress or you pull, always have a positive potential energy. Right? So in this system, you have combination of gravitational force and spring force together. So you write V equal to Vg plus Ve. Vg refer to gravitational force. E referring to elastic, spring elastic energy. So here you can see that your gravitational energy Ws, right, or mgh, right, mgh. W is your weight. your y, or in this case, it give you the s displacement, but this one is below datum. That's why you get a negative energy. All right, just be careful. Gravitational always referring to datum. Okay, if object above datum, you get positive sign here. If the object below datum, you get negative. So spring always positive, half ks square energy. This energy equation won't we won't give you in the exam, so we need to familiar with this equation. So this is the setup of the question. So what happens if you move the particles from S1 to a lower position S2? So the work done by the system, the work done by the work and the spring is V1 minus V2. So you have this equation. I believe just now, I think I need to done correction on my slides here. I think this one is negative, V1 minus V2, but yeah. But anyway, it just depends on the question. So if you look at this setup here, so if the particle move from S1 to a lower position S2, meaning this is S1, and if further move down, what happened to the work done? Work is V1 minus V2. Okay, V1 minus V2. How you get V1 minus V2? You think back of the energy equation, right? So the work done actually is the differences of energy that involve, right? So from the work itself, the total work done by the system actually is the differences of energy. Before this, we look at kinetic energy. You still remember T2 minus work equal, T1 plus work equal to T2 that we look at previously in this chapter. So same concept apply here, but here we look at potential energy rather than kinetic energy. So here we look at potential energy, spring, and gravity. So here we take V1 minus V2. So you take the position 1 and position 2. So as you can see, what happened to the mathematics model? At position 1, you have negative WS1 plus half KS1 square. This is position 1. What happened if you further pull down lower than the datum? You still get negative. All right, you still get negative WS2, but the spring energy is always positive. No matter you pull or compress, the spring will always, potential energy still for the spring, elastic object, it's still positive, plus half ks squared. All right. Correction for the previous slides, that when I show you the differences of equation, it should be negative sign, not positive sign. Right. So this is the derivation of equation. But what is important is that this equation over here, this is the general concept that we always apply, which is if there's a work done in the system, you can find the work done by looking at the change of energy. In this case, we look at potential energy. We use V1 and V2. So when there's a change of energy, potential energy, in this case, spring and gravitational force, then you find the differences of the energy. It will become the work done in the system. So work done equal to the differences of your energy. In this case, potential energy. So the equation of potential energy that consists of spring and gravity give by this equation. Yeah. So if the question give you give you some kinetic energy, then you need to change this equation into the previous one, right? Previous one, look at kinetic energy, but this one, look at potential energy. Okay. Or just give you a hint when you need to use these two equation here. When you have a spring, you have an object, you see a datum in a question. Basically, this is the general equation that we expect in your answer. Okay. When you see cars, you see moving object, that one is the previous section that involved with kinetic energy. But if you see spring, you see gravitational force, you see datum. Of course, gravitational force we won't tell you, but you see datum, you see spring, you see W. But normally we don't tell W in the test. We just give you the weight, the mass of the object. Then you know when you see spring, datum, and mass in the question, basically you fall under potential energy equation like this. Okay. So before I move to the next slide, ask yourself, do you understand why suddenly there's a negative sign in this equation or not? Why there's a negative sign and not positive? Okay, at least you should understand before we move on. You should understand why there's a negative sign and not positive. And do you able to explain to your friend in what scenario your VG, your energy gravity is positive? Are you able to explain? Yeah. The answer is in the previous video. If you are, or I think 10 minutes ago, I just explained why it's positive, why it's negative. Yeah. Okay, we rearrange. This is just a rearrange of equation. So basically, if you understand this one, you understand substitution. The rest is just come by automatics. Yeah. So you move the weight equation, the weight energy equation, W equal to S2 minus S1. If you rearrange, negative become positive. So S2 become positive, negative S1. Here also same, negative multiplied by positive, you get negative. So this is positive, right? Positive half KS1 square. So you want to write in the mathematic form, negative in front of the bracket. What you do, you change the positive become negative. You still get the same presentation. Negative, you get positive. Right? It's just a rearrange of equation from here to here. So as you can see here, what does it tell you? All right. So when you have a change of position, all right, elevation, or you can say as displacement in the air. So S2 minus S1 multiplied by the force itself, or mgh, the one that you learn in your physics, mgh, minus the spring energy, second position minus first position, you get the work done in this system. Okay. So we have done with the gravitational force. We're done with the spring object. Next, we move to an object. What happens if an object that moving in the path that you're familiar with? In this module, I use the blue color to represent path always. So let's say you have an object red color at the starting position in the three-dimensional position. You have x, y, and z in Cartesian coordinate, x, y, and z. And after a certain of time, this object move from this location to this location, and you are given a coordinate system also. X plus dx means there's a certain change of x location, y, and also z. But this object travel in a path, right? So work done, the work done in this system, okay, work done by the system, again, you can write in a potential system, in a potential energy system. So you write the work on the left hand side, work left hand side, the energy difference in the system. In this case, because we look at potential dimension, so potential dimension, you only have gravity and maybe spring force, right? So V1 minus V2. So you put in expand the position. So this is just a mathematics presentation. Du means the change of energy inside the system equal the energy at first position minus the energy at second location, right? Don't confuse with the notation here. It just means that the energy at first position, bracket, first position coordinate, it is here, minus the second position over here, and this is du. So when you have du one side, all right, du one side, you know that the next steps will be integration, right? Du one side, du one side, or dv one side. You have the differential one side, differential one side. You know the next steps will be integration to find the total energy of the system. So how to from here to here is that you expand this equation. You know that when you see here, okay. So this is just another application. Recall this we call it recycle the concept that we learned previously, FDR, and we write in the vector form. So F is force in I direction, J direction, K direction. So Fi, Fyj, Fzk. What about the R? The R also can write in the ijk location, dxi plus dzy plus dzk. And you know that in vector multiplication dot products, okay, dot products, they must be in the same direction, then only you have work, right? I, then you have work. I, J, ijk, they are all in the 90-degree different, right? So if you have I, J cancel, not cancel, but it becomes 0, right? So what happened if you another side means still same but negative value. So what I want to show you here is that I multiply by I, you will get same direction, then you will get work done. Force by displacement, you get work. So I multiply by J, right? I multiply by J means what does it mean? I and J 90-degree cancel, or there's no work done in 90-degree. So from here you only left out at the end, you just left out f x y dy f z dz. Okay, so this one, when you have three-dimensional cases, you use ijk to represent the scenario. Okay, so I pull the equation up a little bit. So we have du equal to this equation. Du is a work is force and displacement. But in this case, we look at x direction, y direction, z direction in three-dimensional way, right? So you can expand this equation again into mathematic form. Again, this is mathematics. It doesn't link with dynamics here. It's just a rewrite of this equation here. So as you can see, left-hand side here is actually the same equation of previously we derived. F dx plus y dy plus fz dz equal, you can rewrite in the partial differential derivatives. You stay as dx, you stay. I mean, this one you rewrite dx, dy, dz, you still remain in the equation. Dx, dy, dz. What change is your force? Right? What change is your force? Is del v over del x, del v over del y, del v over del z. Again, what is v? V is energy. V is energy. So how to find force? Okay, force is defined by the partial differential of energy over distance or over displacement. And observe the symbol that we use for in front of this one. This one is d. Dx. This is del. Is an inverted six symbol, right? It's an inverted six symbol, which is, it means that very, very, very small changes of that dimension. In this case, very, very small changes of your energy in x direction, dx, right? So this is just a mathematics presentation. Okay, so I move this equation up a little bit. Right, we just rewrite this equation into partial differential derivative equation. So as you can see here, this one equal to this one, but with a negative sign in front of the bracket, yeah? With a negative sign in front of bracket. Okay. And so on. The rest is same. Fy, same with this one. Fz, same with this one. So we can rewrite all this on the left-hand side first, because we will further derive the equation. Remember, there's a negative sign there. Yeah? There's a negative sign there. So we have fx, fy, fz. Copy from this three colors line here. This one equal to this one. This one equal to this one. This one equal to this one. So we can simplify the equation behind as f equal to fxi plus fyj plus fzk. Or in other term is that you can change your force equation into your energy equation. Right? Del V is energy, del V is energy, del V is energy, but in each respective direction. X direction, Y direction, energy in potential energy in X direction, the change of energy in Y direction, the change of energy in Z direction. So basically you can define the force into energy, but with the negative sign, yeah? And you can, this is again mathematics, you can pull the upper object here outside to become bracket V, right? So if you factor out the V and you write as del something plus del something plus del something, del over del x, del over del y, del over del z. Again, this is del, inverted six symbols. Del, it means very, 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 very small changes in the system, in x direction, y direction, and z direction. This symbol will be used to represent this one, this one, this one. Okay. So this is called vector operator. This symbol is called vector operator, which is del x, del y, del z with I, j, k in front at the back. We call it vector operator. Okay, so when you see me in your final year subject or in other subject at your final year, you will see this member again um, with inverted triangular here. You'll see this one in finite element analysis, FEA. You'll see this one in your um, things that need to find in the changes in x, y, and z direction in three-dimensional direction, right? So in later chapter in this module, you will see this symbol again, right? This inverted vector operator, right? Inverted triangular. Just remember this symbol there. So because later we will not repeat writing this one anymore, but we will straight away use this inverted triangular symbol in our calculation. Right? It means vector operator. Or there's one very famous equation called Navier-Stokes equation. Navier-Stokes equation, when you learn about high-level analysis in FEM or FEA, finite element analysis, then you see a lot of these things. Or maybe some, if you study about heat transfer, then you have this inverted triangular in your calculation. Okay. Okay, so we summarize what we learned before this. So we talk about, when you talk about conservation of energy, you know that you have two type of energy that you learn up to today. You learn about kinetic energy, you learn about potential energy. So if you don't want to miss any energy in the system, you put all the defined energy in one equation, which is T1 kinetic energy plus potential energy plus the work done in the system, which is non-conservative work done by inside the system. You put on the left hand side, equal to the change of energy on the right hand side. T means kinetic energy, V means potential energy. Before today lesson, you learn about T1 plus work equal to T2. This is before today lecture. After today lecture, when you solve equation in the test or final exam, this is a complete equation we expect when you solve chapter 3 question. Kinetic energy plus potential energy plus work equal to the final potential energy, kinetic energy. Right? So if the question in one of the question it states only consider conservative work is done in the system, then you can remove this piece from the equation, because if you only consider conservation of force, you can consider this one, you can take out this one. Then you have kinetic energy plus potential energy before the incident happened equal to kinetic energy plus potential energy after the incidents. Right? So this equation also serves as definition of conservation of energy, where energy cannot be destroyed, but it can change form to another form. Right? This one is called as conservation of mechanical energy or conservation of energy. That is what you learn in your physics. Yeah? Right? So kinetic plus potential before or at the initial position plus the kinetic plus potential at the last position or final position. This one only works when you only consider conservative forces inside the system. Conservation force that do the work. Huh? What does it mean? If you recall back, there's one forces in the system that we mentioned just now in my slides that is not conservative. That is not conservative, which is the friction force. Okay, so if the question asks you to only consider conservation force in your calculation, you done this part, you have to redo the new calculation by taking out the friction force to balance the energy equation. Okay, both are valid, but both work for different scenario. Huh? This one in the whole system by considering non-conservative work done in the system. However, this equation only works when you consider mechanical energy or you only consider conservative forces that work that done the force. Then you use this equation. Okay. Look for a few more slides. So give you an example. If you again, if you use T1 plus V1 means kinetic energy plus potential energy before or at the initial position equal to energy after or final location. This one only works when you consider conservation of energy in the case. Huh? So you will see if the question state already, by referring to conservation of energy, calculate something. It means you use this equation. Huh? So as you can see here, there's a ball here. All right, ball here. So you can see there's under conservation of energy, kinetic energy and potential energy change from location to location. So at the middle here, the ball that dropping from the sky at maximum height h here, at the center location where h divided by 2, center location, kinetic energy and potential energy will be equal. However, at the below, where the ball reach below, potential will be 0 because of the elevation, and kinetic energy will be maximum. And when the ball, before it release from the rest, kinetic energy will be 0 because kinetic energy equal to half mv square. So there's no velocity before start, so kinetic energy 0. Potential energy will be maximum because potential energy equal to Wy or mgh, like what you learned in your physics, right? So it will be maximum when before it start. And just give you a hint. Every time you in the question you see datum, it means you need to consider potential energy already. Yeah. So in this case, datum and the object, the position check. Datum, object above datum, you get positive energy. If this datum, I put it up here, this one become negative because if the object below the datum, you get negative energy, negative potential energy. Be careful on datum. I keep stressing on the datum line here, so it's very important. Check position of object and datum. If the object above datum, you get positive energy, potential energy. If the object is below this datum line, you get negative. If this ball is below here, datum here, you get negative potential energy in your equation. Yeah. Okay, the rest I just explained just now. So so the energy, the total mechanical energy, or another hints in the question. It will ask you determine total mechanical energy in the system. Means straight away use this equation. So at the initial position here, E equal to T1 plus V1. So you know that at this initial position, the ball doesn't move. Kinetic 0. Potential energy, because of the elevation from the datum, you get positive WH equal to WH. Energy before or at the initial position is WH. What is the unit of energy? Energy is watt. Sorry, power is watt. Energy is also, you can use watt. So what happened at the half? Okay, so when you following at the half, the speed can use by this Newton motion equation. Okay, remember this new 3 Newton equation. V equal to VO equal to half AT. This one is the second one. V square equal to U square plus 2A S, and now another one is the displacement one. So there are three. That one is covered in chapter 2 or chapter 1. So go and find out. These are very popular equation. So to find the velocity at here, which is half of the h here, you use this equation. V2 equal to V naught square plus AC y minus initial y. Again, when can you use this equation? Only when you have a constant acceleration. When there's a change of acceleration, this equation doesn't work. Okay, that's for your info. In this case, gravitational force is acting on the object. Gravitational force always constant. So you can use this equation. AC become G. Y, the change of Y, it become H divided by 2. Velocity 0. So your V2 become square root of GH. So just continue. So we already find just now your acceleration and so on. So from here just now, we find that V equal to square root of GH. So go back to the energy equation at that position. So in this case, by using the mechanical conservation energy, energy equal to total energy in the system equal to the kinetic plus potential energy. So here at the middle here is half mv square plus your potential energy is mgh. In this case, your h is half w, right? wh. In this case, at the middle is h divided by 2, mgh divided by 2. You will get, okay, you rewrite w in the term of w divided by g, or you can write your equation in the mass if you want. So you can change this equation over here into here. Okay, so half m v square. What is your m? The mass here you link with the weight. So weight equal to mg, m equal to weight divided by g. So substitute this one inside here. You get w divided by g. How to find your v at this position? By Newton motion equation that we derived just now. V square equal to v naught square plus a 2a y. You get this equation. After you rearrange, you get your v. Substitute your v at this location here. And remember there's a square there. So bracket square. And you know that when you have a square root and square, the head here will be missing, can be removed. And at this location, potential energy equal to WH divided by 2. So by looking at this equation, this square root hat cancelled because of the square. Then you get GH. Here you have G, cancel the G. So here you have half WH. What is W? Half mgh. Here, what is your W? W equal to mg, h divided by 2. So mgh divided by 2. So half mgh plus m plus half mgh, you still get the same energy. Okay, you still get energy at the center there, still equal to WH, because half here, half here. You prove that there's no change of energy here before, center, and at the last one. So at the last one, you apply the same mechanical energy also. Okay, same mechanical energy also. Okay, so just before it hit the ground, you know that by logic, you know that kinetic energy become maximum, but you don't know what is the speed of that before it hit the ground. What you do, you use again equation of Newton motion, the motion equation derived by Newton. So v square equal to v naught square plus acy minus y naught. So here you know what is your height here. Let's see. Yeah, okay. So this equation derived from this position to this position and not this position. So this equation, you're using equation of Newton. So V, final velocity, initial velocity, but this one you are referring to the middle position and not this position. So you are moving from here to here. So you are using this Newton equation here. V square equal to V naught, which is the velocity at this point, which is square root of GH that we find just now, equal to A and the change of height. This is from here to here and not from here to here. So from here to here is half h squared. So that's why here your equation become 2ac here is gravitational force. So ac become g, h become the elevation change of position become h divided by 2. Okay, so here you square, the head will be gone. So you get gh. Here 2g h divided by 2, 2 cancel 2, you get gh. All right, so this gh plus gh, you get 2gh, and you move the square on the left hand side to right hand side, you get v equal to square root of 2gh. This is the speed before it hit the ground. Okay, so this is a very simple derivation from Newton equation. Okay, so at the, okay, so I think there's a typo error here. It's not a mid height, but it's at the position when it strike the ground, before it strike the ground. So this one I label as T3 V3, but this line here a bit wrong. It's not mid range because I copy from the previous slides. It should be at the before it struck the ground there. So you know that P is kinetic energy, half mv square. This is V3 is potential energy, so it's mgh. So you know that when it before it hit the ground, the H is 0. So potential energy don't have, but you only have kinetic energy. So again, you rearrange your equation. M become weight divided by G. Okay. So you know that kinetic energy equal to half M V square. So M is W divided by G. Why we need to rearrange? Why we need to go so many steps to rearrange become W by G? Because your velocity here is in terms of G and H. So you need to cancel the equation, right? So V square is here. V square equal to this one. Or you can write this one, right? Actually the same, right? So, sorry, V square equal to this one plus this one. But V equal to square root of 2GH. So 2GH square, bracket square. So cancel the head. So when you cancel the head, 2 cancel 2, G cancel G, you get WH. So WH. So from the 3 slides before this, at initial position, the energy equal to WH. At the middle position, energy equal to WH. Before it hit the ground, energy become also WH. This equation, it proves that the energy is conservative. If you use this equation, this equation only works when the energy is conservative. Okay. As we go deeper, when we consider drag in the friction force in the air, this one doesn't work anymore. If we learn deeper later on, when we consider the drag force in the air, when this ball in the question, I add in one more parameter where it asks you to consider friction force between the ball and the air. I give you the friction coefficient, then this equation doesn't work anymore because friction force is fall under non-conservative energy. Okay. Okay, so this is just okay. So I think we stop here and then we continue tomorrow. Let me stop the recording. Any questions?